In 1896, we thought the atom was the atom. The Dalton solid sphere model of the atom said that this atom is different from that atom, but basically they all boil down to billiard balls or marbles. They're indivisible. They're as small as they get. But in 1897, J.J. Thomson discovers that that's not true. He discovers in 1897 that there is something smaller than the atom itself, and that is an electron. Now, we know now that there's protons and neutrons, right? J.J. Thomson didn't know anything about protons and neutrons, but at least the discovery of something smaller than the atom is something. Now, how exactly did he make that discovery? That's what we're going to talk about today. J.J. Thomson used a device called a cathode ray tube to discover the electron. A cathode ray tube is, how many of you guys have in your basement or your bonus room or something, one of the old style like TVs that weigh literally a ton? They're about that thick and they weigh, you got to have two people to carry it down the stairs. How many people have one of those still? You can't buy them anymore, right? But some people still have one because they still work, right? Those are based on cathode ray tube technology, although, of course, J.J. Thomson wasn't watching TV while he was doing an experiment. He was just performing whatever kind of experiment, I'm not sure what it was, with the cathode ray tube when he noticed something happened to this beam within the cathode ray tube. Let me draw it here. This is a basic cathode ray tube, like the tube that's inside one of the older style CRT, really heavy TVs. This is the screen over here. Inside, and this is the tube right here. This blue part is the tube right here that is literally just a glass tube that has all the air sucked out of it. It's evacuated. It has all the air sucked out of it. Now, at one end of this glass tube is an electrode. Now, this is a bit of a simplification because the reality is you're not going to just have a battery hooked up here. You need a really, really big potential difference, and you're going to accomplish that by a transformer. But you need a potential difference, okay? That's not the point of what we want to talk about here today. Be a big potential difference, but it's just a potential difference. We have another electrode over here, got a little hole in it, and you'll see why it has a little hole in it in just a second here. Okay, this is the negative end of the battery. This is the positive end of the battery, which makes this electrode negatively charged, and this electrode over here positively charged. Now, if we build up a big enough potential difference across that gap, then we can get electrons literally to jump from this negative terminal towards the positive terminal. Now, remember, we know that electrons will jump from the negative terminal to the positive terminal, but remember that Thomson didn't know anything about electrons. We knew about charge at this time, positive, negative charge, but we didn't know where it came from, electrons, protons, or otherwise. So Thomson fires this thing up, and something is leaving this negative terminal and going toward the positive terminal. And it keeps going through because we got a hole in that positive terminal, so it keeps going through and strikes the screen. He's able to determine where it strikes the screen because the screen is painted with a phosphorescent coating, which means that when something like beam of electrons strikes it, it glows. That's why your old style TV in your basement shows a picture, because beams of electrons strike the screen in a certain spot and cause the paint on the backside of the glass to glow. Now, lots of people prior to Thomson had observed this. Lots of people had seen this mysterious beam going from this negative terminal to the positive terminal, but nobody knew what they were. They called them cathode rays because they left and this is going to be confusing if you've taken chemistry, because they left the cathode and went toward the anode. Cathode rays left the cathode and went toward the anode. We call the negative terminal the cathode. Cathode rays, mysterious. What is it? Some people thought it was electromagnetic radiation. Some people hypothesized that maybe it was some kind of charged particle, but nobody really knew what they were, and nobody had any proof for their theories of what they were. So this is what Thomson does. Thomson introduces a magnetic field into the mix here. Puts a magnetic field down here. We've got this magnetic field drawn into the page. Tell me, what's going to happen? What do you know will happen to this mysterious cathode ray that we now know are electrons? What's going to happen when exposed to this magnetic field, Ollie?
It's going to emit EMR.
No, it's not going to be the EMR. Yeah, they're going to experience a deflection force downwards, right? Thumb in the direction of the particles, fingers field, palm points downwards. Now remember, we're working backwards here, right? Thomson, when he was doing this experiment, he didn't say, oh, these particles should go deflect downwards because of this magnetic field. Thomson introduced the magnetic field and noticed that the particles were deflected downwards. And he concluded something from that. He concluded that these were beams of negatively charged particles. That's still not the discovery of the electron, but it's something. These mysterious cathode rays that people had observed for 40 years are now beams of negatively charged particles because of the way they deflected in a magnetic field. And some of you are thinking, well, how do we know that negative particles deflected in a certain way in a magnetic field when we didn't know electrons existed? Okay, we knew about charge for decades. Remember, in 1819, Oersted discovered that moving charges generate magnetic fields. Okay, we knew from the early part of the 19th century about a relationship between electricity and magnetism. We just didn't know where the charge was coming from prior to 1897. That's all. We knew it was there. We just didn't know it was due to electrons. So this isn't a big deal. I mean, this isn't like he didn't discover that negative charges deflect in a certain way in magnetic fields. That was well established. He just discovered that these beams, these unknown cathode ray beams, deflected in a magnetic field, and therefore he concluded they were negatively charged particles. Well, now that he knows they're negatively charged particles, he figures I can do a bit of an analysis on this. You guys could do this analysis too, for that matter. You guys know that when a charged particle goes in a magnetic field, it moves in a circle, as long as it's exposed to the field. Therefore, it's a centripetal force. But that centripetal force is equal to the magnetic force. So we'd say Fc is equal to Fm, or mv squared over r is equal to qvb. We cancel out a v, I guess. Cancel out a v, and we're left with mv over r equals q times b. All right, good. What's m? Thomson didn't know what m was. Like, how heavy are these negatively charged, mysterious cathode rays? Don't know. What's v? I don't know that either. How fast are they moving? Don't know. What's r? Well, he could determine r by where they struck the screen, right? We know where they strike the screen based on where the screen glows, and then from that we can determine r. So, okay, 1 for 3. We don't know what m is. We don't know what v is. We know what r is. What's q? We don't know. What's b? Well, he introduced the magnetic field, so he could pretty easily determine what the value of b was, right? So he knows two things. He knows r, and he knows b, and he doesn't know anything else. Well, that's not very helpful. Is it, Christian? So now he does something else. Now he introduces another magnetic field over here a little bit. That would cause the particles to deflect downwards as well, except that he also at the same time introduced an electric field caused by these charged parallel plates. There would be a magnetic force downwards, and there would be an electric force on these cathode rays upwards. Now, depending upon the speed of these particles, one force may be bigger than the other. If the electric force is bigger, then the particles will be deflected upwards. If the magnetic force is bigger, they get deflected downwards. But if the particles are going at the right speed, then those two forces will be equal. And these particles, these mysterious negatively charged cathode rays, will go straight through undeflected. So this is what he starts analyzing now, is these particles that go through undeflected. The ones that go up or down, we don't care about those. The ones that go straight through, we know that Fe equals Fm. Electric force equals magnetic force, or Q times E. Remember that equation? E is equal to F over Q, rearranged, equals QVB. Q's cancel, and we end up getting V is equal to E over B. So now look at it. We don't know the speed of all the particles, but we do know the speed now of the particles that go straight through, because the ones that go straight through have these two forces balanced and therefore have a speed of E over B. Now he can take this equation and plug it into there, got the speed. Now he doesn't know what M is or Q is, but he's just tipped the balance a little bit, right? He had 2 givens and 3 unknowns. Now he has 3 givens and 2 unknowns. He still can't find what Q is, and he'd like to, because he knows these are charged particles. He still can't find what M is. But he can find what the ratio of those is. Somebody walks into the room right now and says, Mr. Dickie, how old are you? And I said, I'm not telling. And then somebody says, Kyle, how old are you? Kyle says, I'm not telling. And the person says, well, come on, I just want to know your ages. And Kyle says, well, I'll tell you what. I'm not going to tell you how old I am, but I'll tell you that the ratio of Mr. Dickie's age to my age is 2 to 1. Well, that's not what the person wanted to hear, right? The person wanted my age and Kyle's age. But the ratio of my age to Kyle's age is at least something for that person. The person knows more leaving the room than they knew coming in, right? So, although we can't find Q and we can't find M, we can find the ratio of Q to M, which is not what we want, but it's something at least. So what we're going to do is divide the right side by M, and take the M over by dividing to the right side, take B over by dividing to the left side. We get Q over M is equal to V over BR. There's the ratio of the charge to mass. So again, we want the charge, and we got the charge later on, not through this experiment, but as we talk about tomorrow. We got the mass as well later on, but for now, we're going to have to be happy with just having the ratio of the charge to mass. By the way, the value for that, I believe, worked out to be, don't quote me on this number, but I believe it was 1.76 times 10 to the 11 coulombs per kilogram. Bottom line is, it's a big, big number. It's a bigger number, in fact, than any other. This is the crux of the discovery of the electron, so pay attention to this, okay? This is a bigger number than any other charge to mass ratio ever measured. Nobody had ever measured the charge to mass ratio of any atom or anything to be bigger than this number. So, what does Thomson conclude from this? Okay, the big takeaway. What does Thomson conclude from this? Well, if Q over M is big, then M must be small. If this is bigger than any other number ever found, then this must be smaller than any number ever found. Hence, we don't just have negatively charged particles. If this M is smaller than the mass of an atom, then this negatively charged particle must be smaller than an atom. It must be a subatomic particle. So now we've got the discovery of the electron. Now we know that these cathode rays aren't just negatively charged particles, but rather they're negatively charged subatomic particles. Does that make sense? Big number there, small mass, bigger number than any other atom or anything charge to mass ratio ever measured, therefore smaller mass than anything else ever measured, therefore subatomic. Ollie? Or sorry, Ethan had the first question there.
So did Thomson have these equations, or did he have to make them?
No, he didn't have to make these up at all. Now, he derived, say, this equation because in this situation he had an electric field and a magnetic field, but he knew the equations for electric force and magnetic force and centripetal force. That was all well established. He didn't discover any of the mathematics or even not even really any of the physics of the experiment. That was for upwards of 100 years almost around. But he was just the guy that okay, measured the charge to mass ratio for these cathode rays and then interpreted the result of that to discover the electron. We say discover the electron, right? It doesn't mean he was the first guy to see them. He was the first guy to realize that he was seeing it. Yeah, that's a good way to put it. Yeah. Oh, you had a question?
So I'm just trying to think though. He was trying to prove there's stuff inside the atom.
Yeah. Well, he wasn't necessarily trying to prove there was stuff inside the atom. He was trying to figure out what these cathode rays were. Like these mysterious cathode rays that were going from the cathode to the anode and beyond that people had observed for 30, 40, 50 years, but couldn't figure out what they were. So he wasn't necessarily trying to prove they were subatomic particles. He was trying to find out what these things were, and it led him to conclude that they were subatomic particles.
Would that number always show up though?
1.76 times 10 to the 11?
Yeah.
Yeah. Or a number that was close to that at least. Okay. When he takes the speed of the particles that were moving undeflected in this section, divided by the magnetic field strength here and the radius of the path here, regardless of, even if these numbers changed, these numbers can change all they want, but combined, they always give me this. For an electron, right? For some other charged particle, they give me something else. But for yeah, he could. Sure, he could. Yeah, they would. They would go upwards in there, although they would still go undeflected here because you see the charge cancels. Okay, so if you sent protons through there, you would find they would be deflected upwards. You could do the same analysis, but you would I don't know what the charge to mass ratio of protons is, okay, off the top of my head, but I do know that the charge to mass ratio of protons would compare how to the electrons, bigger or smaller? You tell me, bigger or smaller charge to mass ratio for protons? It would be smaller. Yeah, it would be smaller. And why? Because the mass of the protons is bigger, right? If this number, this charge to mass ratio number is smaller, then the mass must be bigger. And we know the mass, now at least, we know the mass of a proton is bigger. Keep in mind that he didn't have any concept of protons existing, right? Prior to this, we didn't have any concept of any subatomic particles existing. It came later. Protons and neutrons came later on. No, not a Nobel Peace Prize. I don't think so, actually. I don't think. Does that make sense? Kind of make sense, guys? All right. You're responsible for being able to do either analysis, but in the end, this is kind of a good way to start a new unit because it leads us to a conclusion that there's subatomic particles called electrons. But in the end, we've done all this stuff before. It's just the context in which we're doing it, right? This we've done a million times before. Fe equals Fm, we've done before, not a million times, but we've done it before. It's just, again, a matter of how you put it all together and how you interpret it. Now, there is one more thing that you see every once in a while here, although not all that often. In this first section over here, we occasionally have to analyze that. And how would we do that? Well, if we have a charged particle accelerating from the cathode to the anode, what do you think we'd do? A charged particle accelerating from the cathode to the anode. When a charged particle speeds up, what have you done? I know it's been a while. Charged particle speeds up. Don't we just do EI equals EF? Electric potential energy gets converted to kinetic energy. Why don't we just use the speed from this into here? Well, because the reality is these charged particles accelerate. This equation assumes that it's 100% efficient and that the final kinetic energy will be equal to the initial, and that's not always the case. So what we're saying here is that this speed that we calculate right here is not necessarily the speed that they leave the anode at. We're saying that's the maximum possible speed, really. This doesn't give us the maximum possible speed. This gives us the exact speed that they're moving. So if you have to get a speed from this to plug into the last section, Okay, you can do that, but understand it's not necessarily the speed they're moving, just the maximum possible speed. A better option, if you can do it, is to get the speed from this section right here. Yep. I would say they discovered them. Yeah. Yeah. I would say that, um, I don't know, maybe it's semantics, but Peter's question was, and not just for this topic, I think it could be applied to anything, right? Did people invent these equations or discover these equations? Well, even if these equations didn't exist before, they really did exist. They just weren't written down in a form, right? Nature says that electric potential energy gets converted to kinetic energy, and somebody just figured out how to describe that at some point. So they just discovered it as opposed to invented it. Mathematics is just a language, right? Good. By the way, some names that we're going to apply to these just so that we're speaking on common ground here when I talk about this. We'll call this first section the acceleration chamber. That's just my name for it. That's not an official name, but that's what I'll call it whenever I'm referring to this section where the electrons or cathode rays, whatever you want to call them, accelerate from the anode to the cathode. We'll call this middle one the velocity selection chamber. That's not my term. That's pretty commonly used, actually. The velocity selection chamber, where a certain velocity or speed is selected to keep going into the third section that I call the main chamber. Again, just my name for it. So we accelerate, EI equals EF, and then we go through a velocity selection chamber where the electric force equals the magnetic force, and then we go into a main chamber where the forces don't balance, but they're equal to each other because the magnetic force causes the centripetal force. And then ultimately, we end up solving for Q over M. What does the model of the atom look like that Thomson came up with as a result of this? Well, listen, we had the Dalton solid sphere model of the atom. Now we know there's something inside it. Thomson was way, way off on what these electrons do and where they are and what they look like and so on. But at least he recognized that they existed. Thomson said that the atom consists of a sea of positive charge. Like, you're in Vancouver, there's the harbor, the water is the sea of positive charge. It's not a bunch of little individual positives moving around. It's just a sea of positive charge. You got chocolate chip cookies, the cookie dough would be the sea of positive charge. You have raisin buns, okay? The buns, the dough would be the positive charge, the sea of positive charge. But inside that sea of positive charge is a bunch of little electrons, negative charges moving around, floating around. Okay. All these little negatively charged subatomic particle electrons floating around in the sea of positive charge. Plum pudding model, raisin bun model, the Vancouver harbor model, if you want, like call it whatever you want. By the way, what would be analogous to the electrons floating around if you're talking about a harbor model of this? Yeah, little boats floating around in it, right? Boats would be the electrons, the water would be not the protons, but the positive charge. Clearly, nowhere close to what we currently accept as our model of the atom, but at least it's better than we had before because there's subatomic particles here. All right, let's take a look at a problem on page 756. Notice chapter 15 here now. Getting there. Beam of electrons passes undeflected through a magnetic field combined with this electric field. The electric field, the magnetic field, and the velocity are all perpendicular to each other. How fast are the electrons traveling? Hey, this is a cathode ray tube problem, but you got to ask yourself here, if you've got electrons or cathode rays going undeflected through an electric field and a magnetic field, which chamber of the cathode ray tube is this? Which section is it? It's not good enough now just to say it's a cathode ray tube. Let's analyze it like that. Hey, this is really three problems in one. Which chamber is it if the particles are going undeflected through an electric field and magnetic field? Julia? It's the velocity selection chamber. Okay, because here's where we have the electric force and the magnetic force, and the particles are going undeflected. So look for those keywords, right? Undeflected. Look for an electric and a magnetic field together. If we just had a magnetic field, what would it be? If it was just a magnetic field, it would be the main chamber. Then they're going to go in circles. If it was just an electric field, what would it be? The what? The acceleration, yeah. The acceleration chamber, right? Because the electric field or potential difference caused them to accelerate. Then they go through an electric and a magnetic field, and then they go through just a magnetic field. This is the velocity selection chamber where we can say the electric force is equal in magnitude to the magnetic force. We can say Q times the electric field is equal to QVB, B being the magnetic field. Q's cancel. So even though we are dealing with beams of electrons, Kate Thompson didn't need to know that when he performed this experiment for the first time, because the charge cancels. V is E over B. The electric field here is 50,000 newtons per coulomb, 50 kilonewtons per coulomb, divided by the magnetic field of 0.50 Tesla. We do the math there, and I think it works out to be 1.0 times 10 to the 5, I think. Somebody just double check that math. Some of these electrons, these mysterious cathode rays, would probably go deflect upwards. Some would deflect downwards if they're going too fast or too slow. But the ones that are going this speed will go straight through. And those are the ones we care about, because those are the ones that are going to enter the main chamber, and we're going to analyze to find the charge to mass ratio of. All right, let's have a look at these three questions on page 756. And a reminder, clearly these are going to be cathode ray tube questions, right? But don't just accept that. Okay, when you look at each question, stop and think, oh, okay, this is why it's a cathode ray tube. And then once you do that, stop and say, oh, is this an acceleration chamber, a velocity selection chamber, or is this a main chamber? Or is it some kind of combination of those three chambers? Okay, let's have a look at question number 3 here. It says, what magnitude of magnetic field will stop ions from being deflected? It doesn't say that it's going to stop ions, right? It stops them from being deflected. They're undeflected as they move through a speed of 75 kilometers per second, not kilometers per hour, kilometers per second, through an electric field of 150. This is a velocity selection chamber where the electric force equals the magnetic force because the particles are going undeflected and we have an electric and magnetic field. We're going to say Q times E is equal to QVB. Q's will cancel. So we've got now, we're looking for magnetic field. Usually in the velocity selection chamber, we're solving for V, but in this case, we're solving for B. It becomes E over V. The electric field strength is 150 newtons per coulomb, and the speed is 75 times 10 to the 3 meters per second, or 75,000 meters per second. Why didn't I divide that by 3.6? Why did I times it by 1,000 rather than divide it by 3.6? Yeah, I already had seconds on the bottom. I only have to convert kilometers to meters here. When I do that, it gives me 2.0 times 10 to the negative 3, which is a reasonable magnetic field, right? Usually a bar magnet is in that 10 to the minus 2 range. The Earth's magnetic field is 10 to the minus 5. The MRI is 10 to the positive 1. So 10 to the minus 3 is in that range where it could be. Which is it? Yep. Good. Let's try one more here. So it says, when a beam of electrons accelerated to a speed of 5.93 times 10 to the 5 is directed perpendicular to a 100 microtesla magnetic field. That's a pretty small one, 10 to the minus 6. They travel in a circular path of radius 3.37 centimeters. What's the charge to mass ratio? Which chamber is this of the cathode ray tube? Yeah, Ethan? This is the main chamber. We have a magnetic field only. We know that they're going in a circle because there's a radius. So we're going to say FC equals FM. Now, somebody asked me, I think it was you, Ethan, about can we use the charge of an electron? When it tells me a beam of electrons, yeah. Okay, if it says a cathode ray, well, then you might have to assume that you're like Thomson and didn't know what charge and mass was. But when it says a beam of electrons, yeah, you can use anything that you have available to you. S equals Fm, we're going to say mv squared over r equals qvb. We're going to say r, sorry, keep wanting to cancel out r there. When v cancels, I get mv over r equals q times b. Now I want to solve for q over m. Take the m down, take the b down, and I get q is equal to v over, q over m I should say, is equal to v over b times r. Listen, if you know q and m, you can just divide q by m. But in this question, they're really expecting me to divide the speed by b, which is 100 times 10 to the minus 6 Tesla, times 0.0337 meters. Let's do this as a group here. On the bottom, let's say 100 times 10 to the minus 6 times 0.0337. And now let's say 5.93 times 10 to the 5 divided by that. Oh, look at that. What do we get? 1.76. 1.76 times 10 to the 11 coulombs per kilogram. Isn't that what I said Thomson found the charge to mass ratio of the electron to be, or the cathode ray to be? You're going to do a couple questions on this in just a second here. What I want to point out before you tackle those questions, though, is that sometimes they'll give you a question where it says protons or ions. Strictly speaking, that's not a cathode ray tube if it's protons or ions, right? It's what we call a mass spectrometer. It can be used to measure properties of a particular ion and sometimes even identify it. But it works the same way. Same chambers, same deal, just that the charge and the mass might be different, that's all. Was there a hand up back here? Yeah? No. We're going to talk about an experiment tomorrow called the Milliken oil drop experiment, which found the charge. And then you can imagine when you have the charge to mass ratio, when you know what Q over M is, and then you find Q, which is what Milliken found, then you can just combine the two results, and anybody can find mass from the two results. So no, he never found Q, he never found M, but it wasn't very long before Q and M were found, just by somebody else. Okay, try those 3 questions, please, on page 758. Those are your homework for tonight. Remember what I said a minute ago, right? Ion, okay, ion, carbon 12 ion. Don't worry about that. Just remember that works the same way as a cathode ray tube. It's not a cathode ray tube, it's a mass spectrometer, but it works the same way, except Q and M are different, that's all. Yep.
That's like cathode ray tube,